Hi everyone, this is Star, and welcome back to this worksheet of CS61B Fall 2019 Week 7. And we just talked about what is asymptotic runtime, and now let's do some examples to get more exercise on the concept. So first, the first question on this worksheet is just to list all the asymptotic runtime from the quickest to the lowest. So remember, as we just mentioned before, there's a couple of rules that you want to remember for analysis for runtime. So first, there need to be a input size, which in this case is all n, so you can treat n as our input size. And the second thing is we want to know that constant does not matter. All right? And by constant, it can either mean a factor or it can be a plus or minus some constant c, as you may see just in a bit. And on that being said, we can go and jump into the very first question. So in this question, we have a couple of runtime expressions. And yeah, just as a side note, what does a runtime mean? So a runtime is basically a function of the input size, right? In our case, n. So you want to see which of this runtime is the quickest and which one is the smallest. So for the very first, we want to know that the smallest runtime is always a constant runtime, and in this case, it's n theta c. So what theta c means is it is a constant, where c is a constant. And remember that, as we said, constant does not matter. So a theta c runtime is often written as theta 1 as well. They are asymptotically the same runtime. And after that, we will have logarithm runtime, which is log n. And some students may get confused why it doesn't specify if it's a log base 2n, if it's log base 10n, or if it's a log or natural log n. All right? And the reason is still the second term, that the constant does not matter, especially in the log case, since logarithm things grow typically slow. So a graph will look at this, right? So even if you change the base factor a little bit, the general runtime does not change that much. Therefore, in logarithm time or in log runtime, we can ignore the base constant. So log n is our next runtime. And our next one is, so typically our next one, or a most common one, is a linear runtime, which is theta n. However, in our case, we have another term here, which is theta to the 0.5, or square root of n. Right? And the reason why square root of n is smaller than theta n, a linear runtime, is a theta n linear runtime is basically n to the 1, right? Versus a square root is n to the 0.5. And some students may ask, okay, why now it matters for the constant? Why we cannot ignore the constant and treat everything the same? And it is because in a polynomial time, it does matter that theta square root or theta n to the 0.5 is not the same as theta n to the 1 or linear runtime, and thus is not the same as a n square runtime. And the reason is obvious, because if we draw it out, we will see a linear runtime like this, and a square runtime will be something like this, that differs really different from a linear runtime. And you can also imagine that a square root runtime will be really slow with respect to the linear runtime. And on that being said, when the constant is at power, which is a power term, we cannot ignore it. Right? So we have a linear runtime and a square runtime. And in between the linear runtime and n square runtime, we have another term that is theta L log n. Right? Sorry, this is a little bit small. I ran out of space. Yeah, and the reason is that since log n is smaller than n, and we can write n squared as n times n. So n times log n is definitely smaller than n times n, since these two are the same and log n is smaller than n. Right? And after that, we can imagine there can be a longer or a slower runtime, that is theta n cubed n to the fourth, so on and so forth. We'll ignore all that in this case because it's not in the question. So the next thing we come across will be a exponential runtime. And in this case, it is 2 to the n. And we also notice there is a 3 to the n, which again, in this case, you could not ignore the constant, because a 2 to the n runtime is really different from a 3 to the n. And it will look something like, for example, if 2 to the n is, when it's 1 is 2, when it's 2 is 4. So it's something like this. A 3 to the n runtime is going to be really different and grow really fast. And you can imagine how it will grow for a theta 100 to the n, for example. All right, so in this case, we cannot ignore it. And therefore, I will add this thing. We cannot ignore the constant if it's at the power term for a polynomial runtime, or if it's the base term for exponential runtime. All right. And on that being said, we go to our next term, which is, after exponential, we have n factorial, which is our next slower runtime. And after that, we have n to the n, as we mentioned before. And the reason is n factorial is basically n times n minus 1 times n minus 2 all the way to 1, versus n to the n is n times n times n times n, which is definitely bigger than the other term. All right? And as you see, there is a really weird term right here, which is really not something that you want to do. It's like horrible. It's horrifying. It's like a thing that you do not want to do at all. All right, and it is n to the n factorial. All right, it is really big because n factorial is bigger than n. So the same base raised to a bigger power will give you a slower runtime. And that's all for the first question.